All right, so today we're diving into a really fascinating paper, one that touches upon a question I think we all instinctively grapple with, just by existing in the world.
Oh, intriguing. And what question would that be?
How about this? How does our brain make sense of space so effortlessly? Like, think about it. We walk into a new room, boom, we instantly grasp the layout, we catch a flying object, no problem, predicting its trajectory in real time. It's a constant stream of spatial information, and we process it with amazing speed and efficiency. It almost feels like magic, but obviously there's a lot going on under the hood, so to speak.
It is a remarkable feat, isn't it? And what's particularly fascinating, and maybe something you haven't considered before, is that this efficient spatial processing might actually be tied to rhythmic electrical activity patterns in the brain. Scientists have been observing these patterns called traveling waves for almost a century now. Imagine actual ripples of neural activity, like waves spreading across the brain surface.
Whoa, really? Waves in the brain? That sounds almost poetic.
It does have a certain elegance to it, doesn't it? These ways have been documented since the early days of brain recordings, going back to the work of Adrian Matthews in the 1930s. Then later, Goldman and his colleagues in the 40s delved even deeper. And the key thing is, these weren't just static points of activity. They were dynamic, propagating waves.
Okay, so you have these traveling waves, but how do they help us understand space? What's the computational role of these waves?
Well, one of the most compelling ideas is that they provide a mechanism for different brain regions to integrate information, which is essential for building a coherent spatial representation of the world.
Right, because local information on its own wouldn't be enough. You need a way to put all the pieces together.
Exactly. And to help visualize this, let's bring in a truly elegant and inspiring problem, one you might find surprisingly relevant. The question posed by mathematician Mark Carrick back in the 1960s. He asked, can one hear the shape of a drum?
Wait, a drum. How does a drum relate to how our brains understand space?
Think of it this way. When you strike a drum, it vibrates, creating waves that travel across the drumhead. And these waves reflect off the boundaries of the drum. Those reflected waves carry information about the drum's overall shape back to the center.
So the shape of the drum influences the patterns of the waves.
Precisely. And these waves eventually settle into stable vibration patterns called normal modes. The really fascinating thing is the frequencies of these modes, the sounds you hear, are fundamentally determined by the drum's unique geometry.
Ah, I see where you're going with this. So are you saying that maybe the brain is doing something similar? Could these traveling neural waves be a way for networks of neurons to encode and integrate spatial information based on those local interactions, much like the vibrations on a drum?
That's the brilliant question that these researchers set out to explore. And instead of physical drums, they used artificial neural networks. Their core approach was to develop and study convolutional recurrent neural networks. They are specifically designed to process spatial data over time.
So they built these networks and tried to see if they could, train them to generate traveling waves in their activity as they processed visual information.
Exactly. And the crucial question was whether these wave-like activity patterns could then be used to perform tasks that require integrating spatial information. Essentially, could their artificial drums make sense of the spatial world through those wave dynamics?
And what did they discover? Did their virtual drums reveal anything insightful about spatial information processing?
Here's where the findings become especially exciting. They discovered that these models, specifically a novel architecture they called the Neural Wave Machine, or NWM, demonstrated a remarkable ability to handle tasks that require a deep understanding of the global spatial context within an image.
So tasks that require seeing the whole picture, not just focusing on isolated parts.
Precisely. And here's the kicker. The NWM not only outperforms standard neural networks that rely on more localized processing, but it also achieved comparable results to more complex architectures like UNets, which are renowned for their global information processing capabilities.
Wow, so it's going toe to toe with some of the big players.
And what's even more noteworthy is that the NWM achieved this level of performance with, in some cases, a smaller number of parameters than those competing models, suggesting it might be a more efficient way to approach spatial integration.
That's a big deal when it comes to designing AI systems. The fewer parameters, the better, right?
Absolutely. So, the goal of this deep dive is to truly understand how this hearing the shape of a drum analogy offers a new perspective on how AI might process and understand the spatial world using these traveling waves. We'll be exploring the innovative aspects of their approach and what this tells us about the potential of wave dynamics in AI.
Sounds like we have a lot of ground to cover. Let's get into it. Now, you mentioned Kalak's question, can one hear the shape of a drum? Let's break that down a bit more.
Right, so remember, striking a drum creates those traveling waves that propagate and are then reflected at the drum's boundary. Those reflections are key. They carry information about the drum's overall shape back towards the interior. The waves interact, they superpose, and they settle into those stable, characteristic vibration patterns, the normal modes.
And those normal modes are directly linked to the specific sound frequencies produced by the drum, correct?
Absolutely. From a mathematical perspective, these normal modes and their corresponding vibration frequencies are solutions to the wave equation under the constraints of the drum's physical boundary. Croc's initial question essentially asked whether this unique set of frequencies could uniquely determine the shape of the drum.
So can you definitively hear the shape?
It turns out the answer is more nuanced than a simple yes or no. While certain properties, like the drum's area, could be determined from the frequencies, a fascinating discovery in the early 1990s revealed something unexpected. Differently shaped drums can produce identical sets of frequencies. They're called isospectral.
So you can't always tell the shape just by listening.
Right. But later research found that specific classes of shapes are uniquely identifiable by their spectral properties. So a significant amount of information about the drum's geometry is encoded in those frequencies.
Okay, so it's complex, but the principle of global shape influencing wave behavior and resulting frequencies still holds. Now, how did the researchers connect this concept to neural networks?
They started with a simple case, a square drum. For a square drum, there's a precise mathematical formulation for its normal modes and their Laplacian eigenvalues, which relate to the curvature of the mode patterns. It gets a bit technical, but essentially the equations describe how the modes oscillate and how their frequencies depend on the drum's size.
So larger drums have lower frequencies, like a longer guitar string producing a lower pitch. That makes sense, but how did they put this into an RNN?
Their thinking was that if a physical drum can integrate global information through wave dynamics, maybe a neural network could too. To test this, they took the wave equation, which governs the drum's vibrations, and discretized it, breaking it into smaller steps suitable for a computer.
So they created a sort of virtual drum within the RNN.
Precisely. They used a technique called fillet integration to simulate those wave dynamics. They defined a grid of neurons, each representing a point on the drumhead, and they used local connections between these neurons to mimic the propagation of waves.
So they had local connections within the RNN, mimicking the physics of wave propagation. But how did they represent the shape of the drum in this setup?
For their validation experiment, they simulated a square drum. They did this by clamping the activity of neurons at the boundary of the square to zero, effectively creating a fixed edge. Then they initiated the simulation by giving the central neuron a little kick, like striking the drumhead, and observed how the activity patterns evolved over time.
So they set up a virtual square drum and let the RNN do its thing. What happened? Did it behave like a real drum?
The results were remarkable. They systematically changed the size of their virtual square and measured the fundamental frequencies generated by the network. These frequencies aligned perfectly with the theoretical predictions for a real square drum of the same size.
Wow, so they had a good model of wave dynamics going on.
Exactly. This validated their approach, showing they could accurately simulate those fundamental wave dynamics. And with this foundation, they move on to a more complex and more relevant to AI problem, semantic segmentation.
Semantic segmentation. For our listeners who might not be familiar, can you quickly explain what that is?
Of course. Imagine you have an image, let's say a busy street scene. Semantic segmentation is about labeling every single pixel in that image according to what object it belongs to. So you mark all the pixels belonging to cars, pedestrians, buildings, trees, and so on.
So it's like coloring in a picture, but with very precise labels for every tiny detail.
Exactly. And the reason this is such a challenge and why it needs global information integration is that you often can't accurately label a pixel just by looking at its immediate neighbors. You need to understand the broader context.
Right, like a small patch of brown pixels could be part of a dog, a tree trunk, or a piece of furniture. You need the surrounding information to make the right call.
Exactly. So they wanted to see if their wave-based approach could tackle this complex task, and they added a twist. They deliberately imposed local connectivity constraints on their models.
Constraints, why would they do that?
They restricted the initial convolutional layers, the ones processing the raw image data, to using small filters, typically 3 by 3 pixels. This means each neuron initially sees only a tiny part of the image, and they did the same for the recurrent connections. Even the final layers producing the pixel labels were local.
So no single neuron had a complete view of the image. They were forcing the network to rely on those local interactions and the temporal dynamics to solve the task.
Precisely. The idea was if the model could successfully do semantic segmentation under these constraints, it would strongly suggest that it's effectively integrating global information through the propagation of those wave-like activity patterns.
It's like a little group of people, each with a tiny piece of a puzzle. None of them can see the whole picture, but somehow, by passing messages back and forth, they manage to put it all together.
It's a great analogy. And this brings us to their special architecture, the neural wave machine, or NWM.
Tell us about it. How does the NWM promote these wave-like dynamics?
Well, the NWM is a kind of recurrent neural network whose mathematical design is biased towards generating traveling wave patterns. Its update rule, which governs how its activity changes over time, incorporates terms representing the local interactions between neurons, their intrinsic natural frequencies, and their damping. But they didn't stop there.
What else did they do?
They made those natural frequencies and damping parameters dynamically dependent on the input image itself. Imagine that the visual input actively shapes how the waves propagate within the network.
That's really cool. So it's not just processing the information, it's also tuning its own internal dynamics based on what it sees.
Precisely. And this allows the network to learn soft boundaries based on the image content, influencing how waves reflect and propagate within its structure. They further encourage wave-like behavior by initializing the recurrent kernel, the part responsible for those local interactions, to resemble the Laplacian operator we talked about earlier, the one that described how waves spread in the drum analogy.
Okay, so we have these waves traveling and reflecting, carrying information across the network. But how do we get from these dynamic patterns to the final semantic segmentation, the actual pixel labels?
That's another crucial innovation, the recurrent readout. They experimented with different ways to extract the segmentation from the sequence of activity patterns generated over time. The simplest was to just use the last activity state, but they also tried more sophisticated methods, taking the maximum or average activity over time, calculating the frequency spectrum with the Fourier transform, and, most importantly, learning a linear projection of the entire activity time series at each pixel.
So they're looking at how the activity at each pixel changes over time, not just its final state.
Exactly. Now let's look at some results. They started with a simple dataset called polygons, which contains images of, well, polygons with different numbers of sides. And what they observed with the NWM was fascinating.
What did they see?
The NWM learned to initiate waves from the edges of the polygons and propagate them inward. And get this, different shapes led to distinct patterns of wave propagation and unique frequency spectra within the shapes.
So it's almost like the network was hearing the shape, just like in Coxill's question.
That's the idea. And they achieved incredibly high accuracies, over 99%, by analyzing those frequency spectra. This demonstrated the potential of these temporal dynamics to encode spatial information for accurate segmentation.
That's amazing. What about more realistic data sets?
They tested on tetrominoes, the shapes from Tetris, and MNIST, the handwritten digits, and they compared their NWM and a standard LSTM against simple CNNs of different depths. Shallower CNNs with limited receptive fields struggled, as expected. Deeper CNNs did better, but were less stable. The recurrent models, especially with that learned linear projection readout, outperformed the CNNs. And the NWM was consistently more stable, showing lower variance in performance across different training runs.
So recurrent models, and particularly the NWM, were better at capturing the global context needed for these tasks.
Exactly. And even the standard LSTM, which wasn't designed for waves, started generating wave-like activity, suggesting this might be a naturally effective strategy for spatial processing under local connectivity.
It's like the network figured out, hey, waves work really well here, even though nobody explicitly told me to use them.
That's a great way to put it. But the real test was a tougher data set. Multi-MS, where you have multiple overlapping digits in each image. This requires even more global information integration.
Yeah, you need to disentangle those digits to segment them correctly. How did the NWM fare in this more challenging scenario?
This is where it really shines. The NWM, with a relatively small number of parameters, around 55,000, outperformed UNet models with similar and even significantly larger numbers of parameters, sometimes having almost 3 times as many. It also had the lowest error rate for segmenting the foreground, meaning it was very confident about where the digits were.
So it was more accurate and more efficient? That's quite impressive.
Indeed. It highlights the potential of this wave-based approach for complex spatial reasoning. The researchers also discussed related work, placing their findings in a broader context. They highlighted the history of wave-based computing and the theoretical framework of neural field theory, which deals with spatiotemporal dynamics in neural systems.
So they're connecting their work to a rich history of research in both AI and neuroscience.
Exactly. They also pointed to recent studies on wave-based RNNs for audio processing, networks with Laplacian operators, and the general area of oscillatory neural networks. But they emphasize that their work stands out by focusing on spatial integration through time and the crucial role of that time series readout, all inspired by Kak's drum question.
It's all about how the network extracts information from the temporal patterns of activity, not just the final state.
Precisely. And they even drew a connection to a neuroscience concept called biting by synchrony, where the brain might associate different features of an object through synchronized activity of neural populations.
So maybe their wave-based approach is computationally similar to how our brains process spatial information.
It's an intriguing possibility, but they also acknowledge some limitations of their work.
What were some of those?
One big one is the computational cost. Simulating those wave dynamics accurately requires a lot of computation, more than simple feed-forward networks like CNNs or UNets.
Right, more computation means more energy, more time, potentially more expensive hardware.
Exactly. And while their models are inspired by the brain, they're still simplified abstractions. Mapping their specific parameters and dynamics directly to biological counterparts is a complex challenge.
So while the drum analogy is a powerful guide, it's not a perfect reflection of how the brain actually works.
Right, it's a starting point for further exploration. And they have some exciting directions for future work. They want to investigate more computationally efficient models that could potentially speed up those simulations. They also want to compare the learned dynamics of their models to actual brain recordings to see how well they match up.
So testing their ideas against real biological data.
Precisely. And they're keen to explore even more sophisticated ways to read out information from those temporal patterns of activity.
So continuing to refine the way their networks hear the shape of the information they're processing.
Exactly.
Okay, so after this deep dive into traveling waves and spatial integration, what are the key takeaways for our listeners?
The main takeaway is that these traveling waves, inspired by the physics of a drum, might be a powerful and efficient way for neural networks to integrate spatial information over time. The key innovation is not just about those waves, but about how information is extracted from their temporal dynamics. That time series readout, especially the learned linear projection, seems to be crucial.
So it's not just about the journey, it's about understanding the map of that journey.
Exactly. What's also exciting is that even standard networks like LSTMs can learn to use these wave-like patterns when dealing with spatial tasks under local connectivity. This suggests it might be a fundamentally effective strategy in these situations. And the NWM's performance on that challenging multi-MS dataset shows the potential of this approach.
So it's not just a new architecture, it hints at a deeper principle about how locally connected systems can process spatial information.
Precisely. And this opens up new possibilities for designing AI that's more efficient and potentially more like the brain. The parameter efficiency compared to UNets is particularly encouraging for building more compact and scalable AI systems.
It really makes you wonder, doesn't it? Could the way our brains use these complex temporal patterns of activity, perhaps through similar wave mechanisms, be the key to our ability to understand the spatial world so effortlessly? This research definitely offers a fresh perspective on both artificial and biological intelligence.
It certainly does. It's a reminder that sometimes the most profound insights come from looking beyond the obvious and exploring the hidden rhythms and patterns that shape our world.
Absolutely. For those who want to delve deeper into this, definitely check out the research paper and related work. And keep an eye out. This is a field with a lot of exciting potential for future discoveries. Oh, hey, our listener wants to join in. What's up? That's an interesting phrase. It sounds like you're asking us to revisit the specific equation that defines the dynamics of that locally coupled oscillatory RNM, the NWM, right?
That's a very astute observation. You're pinpointing the core mechanism we were discussing earlier, how the network's hidden state evolves over time.
Absolutely. So let's unpack this a bit. The paper presents the dynamics of this model with equation 11.
Yes, and that equation, Xiaol.x, is really the heart of how the NWM emulates wave dynamics.
Okay, let's break down the key components for you. The left side, VOOH, represents the second-order time derivative of the hidden state H. Think of it as the acceleration of the network's internal activity.
And on the right side, we have a few crucial terms. The first one, S, involves a convolution operation, denoted by the star, with a kernel who applied to the hidden state H, and then passed through a nonlinearity, S, which in this case is the hyperbolic tangent function.
That convolution, with the kernel initialized to approximate the Laplacian operator as we discussed, is what allows local interactions between the neurons in the network, enabling the wave propagation.
Exactly. Then we have the term LFX. Here, LFX represents the natural frequencies of each oscillator in the network, and importantly, these frequencies are not fixed. They are a function of the input image X, computed through a small convolutional neural network. The odd denotes element-wise multiplication.
So the input image directly influences the intrinsic oscillation rate of different parts of the network, which in turn affects how waves propagate. That's how it learns those soft boundaries we mentioned.
Precisely. And the final term, AFX-LA, is the damping term. Similar to the natural frequencies, the damping factor AFX is also a function of the input image, and the element-wise multiplication is applied to the first-order time derivative of the hidden state, which represents the velocity of the network's activity.
This damping term essentially controls how quickly the oscillations decay in different parts of the network, again influenced by the input.
So to bring it all together, that equation describes a system where the rate of change of the network's activity is determined by local interactions, a convolution, the intrinsic tendencies to oscillate at certain frequencies, influenced by the input, and the dissipation of energy in those oscillations, also influenced by the input.
It's a beautiful way they've translated the physics of wave motion into a neural network architecture, and as we saw, this specific formulation allows the NWM to effectively process spatial information over time.
Absolutely. By learning these input-dependent natural frequencies, damping terms, the network can tailor its wave dynamics to the specific characteristics of the input, enabling that efficient global information integration we've been discussing.
Okay, so with that detailed look at the equation, let's move on to how they actually implemented this in their experiments.
Right. As we touched on earlier, they discretized this continuous wave equation in both space and time to make it computable in a recurrent neural network. This discretization process yielded update equations that are analogous to the steps in an RNN.
And for the numerical integration of this discretized equation, they used a method called fillet integration.
Yes, fillet integration is a popular technique for simulating physical systems because it's computationally efficient and has good stability properties, which is crucial for training recurrent neural networks over longer sequences.
And at the heart of that spatial discretization is the discrete Laplacian operator, which they implemented using a 5-point stencil.
Exactly. That 5-point stencil is a way to approximate the spatial second-order derivatives in the wave equation, essentially, the curvature of the drumhead using the values of neighboring neurons in the grid. It captures those local interactions we were talking about.
So each neuron's activity is influenced by its immediate neighbors, mimicking how waves propagate locally. Now, how did they actually feed the drum or the shape into this RNN?
For the initial validation with the square drum, as we mentioned, the shape was defined by setting the boundary neurons to a fixed value, effectively clamping them.
Think of it like holding the edges of a physical drum tightly.
Precisely. When they moved on to processing images for semantic segmentation, the shape became the content of the input image itself, influencing the natural frequencies and damping terms we just discussed.
So the image wasn't just passively fed into the network, it actively shaped the network's internal wave dynamics.
Exactly. And then, to validate the model's core idea, they conducted experiments where they varied the size of that initial virtual square drum, that length L we saw in some of the equations.
And as we heard, the fundamental frequencies that emerged from their simulated drum matched the theoretical predictions for a physical square drum.
Which was a really important validation of their wave-based approach. It showed that their RNN was indeed capturing those underlying physical principles.
So having